All right, folks. Here's starting the second week here, day 5, and I just want to let you guys know that it's almost going to be a repeat of all the problems we already did, except now we're going to be looking for gravity problems, and there's a distinct difference, and it's pretty much rule number 1 on my sheet. So you'll see on day 5 there's a gravity rules, and if you click on it, um, rule number 1. The big difference is that they may not tell you what the acceleration is. So we're always looking for, does the problem give you acceleration, or is it asking for acceleration? We're looking for that. In a gravity problem, sometimes they don't tell you, and you have to just know, oh, acceleration, that's 9.8 meters per second squared. Specifically negative 9.8 if we're considering downward as negative and up as positive. It is possible to just think of down as positive, and that's fine. We'll talk about that later. But the point is that the acceleration, the amount of it, is 9.8 meters per second squared. That's just how hard, if you release a rock or anything on Earth and gravity starts to pull it down, it'll speed that object up faster and faster and faster with an acceleration rate of 9.8. So that's like rule number 1 right there. But here's the thing: before I even get there to these rules, what, uh, how do you know if it's a gravity problem? And pretty much, if an object drops, falls, or is thrown, it's a gravity problem. Now, not limited to that. For example, if a problem says uh, a rock is tossed off a cliff, and you're like, hey, it said tossed, it didn't say thrown. So what I'm saying is use your imagination here. But if it's something that drops or falls or is thrown or anything even close to that, then in other words, it's an object that's free falling that gravity is going to pull downward. And remember, when you throw something up, gravity pulls it down too. So don't think like, well, they threw it upward, not downward. Yeah, if you throw it up, gravity pulls it down, slows it down, and then it even starts to come back downward after a while, correct? If you wait. So it does pull downward always. Even when you throw something up, it pulls downward. Uh, so know that. And rule number 1 is that A is already given. Even if they don't tell you, A is already known. It's negative 9.8, you already know it. If an object is dropped or falls, it's implied that the original velocity is 0. So you kind of already know VR. They may not tell you, hey, the initial velocity is 0. They may not say that. It'll just say they released it from rest, or they dropped it, or it falls. Like, so if something just falls off a shelf, its starting speed is 0. It was not moving, and it just fell off. So falling and dropping, or from rest, those are all mean initial velocity is 0. So that's another secret hidden piece of information in those problems. Also, if an object drops or falls, the distance it travels will be negative. Okay, so if we're considering down as negative, if it falls 5 meters, then it fell negative 5 meters because it moved downward. It did not move up, it moved down. And we'll consider down as negative now. Okay? So on gravity problems, we'll just consider down always as negative so we don't confuse ourselves. Down will always, anything downward is negative, so acceleration of gravity is down, so that's negative 9.8. And anything moving downward is negative, okay? Anything up is positive. So when an object is number 4, when an object is thrown straight up, let me see if I can zoom in a little bit for you guys. There you go. Look at that. When number 4, when an object is thrown straight up and it reaches its highest point, it is understood that VF is 0. So if I throw something up and it leaves my hand, so if I throw something upward and it leaves my hand with a positive speed, obviously because I threw it up, so it's got positive velocity, the initial velocity is positive. If I ask a question about what about on its highest point, what is its speed? Finally, its speed up there will be 0. It may move on and move from there, but I'm just talking about at that point, its 0. Its speed is 0. So if they just want to know how high something went, if I throw something upward and they tell you what speed it started at, and they go, how high did it go? Well, its final speed is 0. If they're just talking about how high it went, right? Because if they're talking about how high it went, that's all they want to know is there. Does it move afterwards back downwards? Sure, but they don't care about that. They only care about how far it went up. So on those problems, just know that the final speed is 0 if we're talking about something that goes to its highest point. When an object is thrown upward, its initial velocity will be positive. Okay, I kind of mentioned that already. Rule number 6. When an object is thrown down, its initial velocity will be negative. Well, that's kind of common sense. It's the opposite of rule number 5. Rule number 7. When an object is thrown up, the time it takes an object to go up to its highest position is the same as it takes to go back down, if you're coming back to the same place where it came from anyway. That's what it says. Example, you throw a rock into the air and it takes 1.2 seconds to reach its highest point. So you throw it upward and it goes up and it takes 1.2 seconds to get there. Well, then I can tell you it's going to take 1.2 seconds to go down. So it'll be in the air for a total of 2.4 seconds then. So everything going up takes the same amount of time as everything coming down. That's what it's saying. Um, when 8, when an object is thrown up and it comes back to where it started, vi is equal to negative vf. What that means is, all that means is this. It's quite simple. If I throw something up at 10 meters per second, it'll go fast. You throw it up at 10 meters per second, it'll slow down until it stops at its highest point. Then it starts to have negative velocity, so it starts to go down, 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 down until it hits your hand back to where it came from, and it'll be going negative 10 because it's going downward at the same speed as you threw it up. So once again, if I throw it up and it leaves my hand at positive 10 meters per second, that means up at 10 meters per second, it'll be 0 when it gets to the top because it stops technically, and then it slowly starts speeding up, and when it hits my hand back, it's going the same speed but down, obviously not up. So it's negative 10 meters per second. That's all it is. And those are all understood things. These are all the rules that are pretty much understood when you do a gravity problem, and you should know these rules. And keep this sheet nearby, print it or have it out like on a link or something, so that you can always have this during a problem when you're working out your gravity problems. Now, just a quick look. I pulled up some practice problems on a physics site. Let's see which ones are gravity problems. First off, this one is not a gravity problem because they tell you the acceleration and it ain't 9.8, so it's not a gravity problem. A car starts from rest and accelerates uniformly over a distance. Nope, nothing fell, nothing got thrown. Is riding a giant drop. This sounds like it might be. If Upton free falls for 2 seconds, what will be the final velocity when falling? Yep, this is a gravity problem. So we know acceleration already. It's negative 9.8, and we have time, and we can figure this problem out. A race car accelerates uniformly. Blah blah blah. That doesn't sound like that's not a gravity problem. A feather is dropped on the moon. This is a gravity problem, but be careful on this one. It is dropped on the moon, so they had to tell you that the moon's gravity is 1.67. So that is technically a gravity problem. It's just that it's not on Earth, so it's a gravity problem on the moon. But when they do that, they're always going to give you the acceleration. Don't worry about that. So nobody's going to tell you it's dropped on the moon and then like, hey, you should know the acceleration on the moon. No, don't worry about that. Rocket-powered sled, definitely not a gravity problem. A bike accelerates uniformly, does not sound like a gravity problem. An engineer designs a runway for an airport. This is not an acceleration problem. This has got a different acceleration rate. A car traveling definitely doesn't sound like usually a car, unless it's falling off a cliff or something, is not a gravity problem. A kangaroo is capable of jumping. This one sounds like it, to a height of this. Determine the takeoff speed. So there we go. So this is a gravity problem, but this is one of those weird ones that nothing is thrown, but it's jumping. So a kangaroo jumps straight up, I'm assuming, to this height. So we have the distance. They want to know VI, the takeoff speed. We already know VF. It's the final speed is 0. Yep, because it jumps to the highest spot of this, and we know the final velocity is 0. We know gravity is, we know the acceleration rate is negative 9.8. So this one can be solved. We'll work on that one later. Michael Jordan leaps. Yep, here's another one. That was a gravity problem right here if you want to pause it and read it. A bullet leaves, right? This is not one. A baseball is pops straight up into the air. That sounds like a gravity problem already. Not even going to read the rest. Pause the videos though if you want to read them. I'm just kind of going through quickly. Observation of a deck skyscrapers free fall. I see these words. That's a gravity problem. A bullet is moving at a speed. Does not sound like a gravity problem. Okay, so I think that's enough. I think you're hopefully getting the hint of what is a gravity problem, what is not, and then I will do some workout problems step by step, just like I did with the last week. Okay.